Hello, I'm Luke Miller, and this is the Physics 211 Lab 1. This is going to be Constant Velocity Lab. So this is the table of contents. We're going to talk about a quick introduction about kind of what the lab is about, some physics concepts seen in the lab, look at the tracker video data and the model encoded data, and then a quick comparison of those two data sets. Talk about some sources of error, and then answer some additional questions. To begin, the purpose of this lab was to observe and study the motion of an object moving at constant velocity. In this case, it'll be an expo marker, or in the model's case, it'll just be a little blue ball, and then compare some real-life data from Tracker to the data model in Python. The main physics principles at play here are going to be Newton's first law and Newton's second law. And then a quick jump to just the outcome that we're going to see is that if there are no forces acting on an object where they sum to F net equals 0, aka constant velocity, it will just remain moving with that same velocity, which is why it's called constant velocity. And then in the experiment, outside forces cause this number to not be exact because we're going to have friction. We're going to have actual other forces acting there. But in the model, there's no outside force. So the main physics concepts are going to be Newton's first law and Newton's second law. Obviously, first law is at rest remains at rest, in motion remains in motion, in constant velocity, unless something else is acting upon it. And then Newton's second law is just going to be the force acts on something, it causes it to accelerate. In our case, this F net equation is just going to equal 0. And the position update formula will actually be very useful. This will be seen in the code later. So for our tracker and video data, on the left, I just have some important points to point out. We have 17 data points. We have initial position of 0, 0. Initial velocities, now it's going backwards, but as you will see, the graphs I will be showing you will be acting as if this is a positive velocity. And we will talk about later in one of the what if questions, the differences between making them positive and negative in a way. And then the change in time is going to be 0.566 seconds and 0.033 seconds per data point. And then the system in this case is the marker, and the surroundings is the whiteboard, table, and as we talked about in class, everything else in the universe. Obviously, not everything is actually acting on the marker, but it is technically the surroundings. And then you can kind of see our graph on the right side, our position graph, which is where we're going to get some important data points. And then you also can see the y here, which is going to come later as well. So the model code instead is just a literal perfect straight line. And that is because there's nothing else acting on it. So we have our important stuff here. Position, we start at 0, 0. And then the vector we got from before, we just kept it positive this time. And then down here we have the rate, the actual net force, which is 0. The rate is just how fast it's running. And then ball dot velocity, ball dot vel, and vector. So this is like our velocity update. Obviously, there's none of that. And then our position update formula, which just takes the velocity from above and plugs it in since it's not changing. When we compare the data, we see a pretty big difference. The red is our model data and the blue is tracker. Red is a lot bigger, and the line is perfectly straight, meanwhile blue is a lot lower. But we can actually look at why this might be with some source of error. So the main thing that I think actually probably caused this is the force not being precise. Obviously, friction will play a role, but I think force in the y direction, tracker, we can put the axes, try to line up as much as we can, but it's not really going to be perfect every time. And that force in the y direction, as you saw in tracker, was kind of this graph jumping up and down. Meanwhile, the model literally puts all the force into the x. So that's not really an issue. Friction as well. There is no friction in the model. In real life, the table is slowing down the marker as it moves, which is continuing, which is probably why it's slower. And then also tracker and precision, as I mentioned above, axis might be off or just data points might be off. And the final additional questions here. So the what if. So as I said, even though it's going to the other side, I just put all of our things as positive to make the graphs look nicer, up and to the right, a lot more normal looking. But if we flip it, the graphs would just go down to the right, and the data points would just be negative because the velocity would just stay that negative number, but our position would increase in the negative direction. And then what does it mean? We're kind of going to look at, could we find all the forces acting on this? Now, in real life, we know gravity, normal force, and the y add to 0. And we know that the x position is changed by only friction, right? So our initial force at this point has stopped touching the marker, and it's just the friction slowing it down. Meanwhile, the computer model has no other forces acting on it. It is just this ball moving in space with nothing. So it will just continue moving forever. And that's how we would find all the forces acting on it. Anyway, that's been this video. Thank you for watching.